Hello all. In this video, we're going to work through the Colab notebook that I showed you last time and talk about what each step is doing. And these will all be steps that come from the videos earlier that talked about how you go, what is the process for doing supervised learning, and what is it that we do with a convolutional neural network. So that involves getting data, making sure we understand how the data is formatted and checking it to make sure it looks right, doing any pre-processing on the data that we need to do, and then setting up a convolutional neural network and training it and looking at the results. All right, I'm going to take a look at this notebook again, and we'll kind of talk through the blocks block by block. The instructions are in these text blocks for the activity, and I will be elaborating on those instructions in the next before you actually get to the activity. So if we look at this first code block, you can see that it has a lot of import statements. This is fairly typical. It's just nice to have the import statements there. You do see more often with these notebooks people putting import statements later on so that they're close to the part of the program where they're actually being used. That's okay. I'm an old school programmer. I like to have all the import statements all in one place so I can find them when I want them. So you can see we're going to be using the random module. We're going to be using the NumPy module. That's how we represent images. We have 4 lines here that are importing different pieces of Tensorflow. So Tensorflow is the library that's going to let us construct and train deep learning models. It gets imported with a shortened name, like NP for NumPy. We do TF for Tensorflow. We're using parts of the Keras module, which is a part of Tensorflow. It is actually a separate project, but TensorFlow has implemented a version that works with TensorFlow, and that's what we're going to use because it's way easier to understand than the underlying TensorFlow itself. So we are going to be looking at a Keras dataset first, and then we will be using the layers and the models part of the Keras system to define the convolutional neural network. I don't know that we're going to use this image data generator. It's just there in case we need it, but it allows us to do certain fancy things with the data if we need them. And the TDFS or TFDS, I always get that wrong, TFDS, that is a piece of TensorFlow that contains the data sets that TensorFlow itself provides on its website. And we're going to be using one of those for the homework. I also have a couple of import statements that relate to OpenCV. I'm importing OpenCV, but there are certain things that we do in OpenCV that we can't do in a notebook because of the fact that it is running in the cloud. So because it's in the cloud, it doesn't have access to our computer the way OpenCV does when it's running on our computer. That means we can't access the webcam. So we can't read in or display video. It also means it can't pop up windows that you would normally have or interact with like the keyboard or mouse clicks the way that we have done with wait key or the mshow function or other things like that. None of that works when you're running in the cloud because we don't have access to a monitor that's on the computer we're running on. And that computer is halfway around the world from here, doesn't have permission to access your computer. That limits what we can do. Some of the things that we've done that have been kind of fun, we couldn't have done if we were doing them in Colab. But Colab itself provides us with a stopgap measure. It gives us an alternative that we can use. So CV2 underscore mshow is a function that's provided by Google Colab to take the place of our usual mshow, CV2 mshow, .mshow. So CV2 underscore mshow takes in an image represented as OpenCV does as a BGR format, and it displays it in the output box for the code block. It's much clunkier than having something displayed that's, that's in its own window. You can't really do video this way because it doesn't update. It would just show the frames of the video one after another in the output blocks. So it's a little more limited, but it does allow us to use OpenCV fairly effectively even in a Colab notebook. We're using Matplotlib here. That's going to give us another way to display images, basically, and we can also display other kinds of graphs as well. You are not going to need to learn the details of how Matplotlib works. We just have some code samples and you'll copy them and make a few changes as directed by me. The last thing we're doing is we're not actually using scikit-learn. It's a nice Python library for doing more traditional kinds of machine learning. We're not touching that, but it has this function, train test split, which is really nice and doesn't really have an analog in TensorFlow. It basically, if you give it an NumPy array or NumPy arrays that represent your data set, it will automatically split it in a very nice way into training and validation data for you. Super handy. We like to have it, and so we're going to use it in a few places. All right, let's look at what our task is. So what we're going to be looking at first is this CIFAR10 data set. This is a standard data set. It's almost a benchmark. And there's a bigger version of it called CIFAR100, which I suspect is the original. CIFAR100 has 100 different categories, and these are all relatively small images that we'll be working with, 32 by 32 color images. And they are pictures of objects, so animals or vehicles or, I don't know, common everyday household objects in the larger data set. CIFAR10 selected 10 categories, and you'll see they're kind of an odd collection, but fundamentally we have pictures of objects, and it's supposed to predict correctly what category of object is it. Is it a horse? Is it a deer? Is it a car? Is it a fish? Whatever the categories happen to be. You might notice this is seems pretty large. We have 60,000 small images of vehicles and animals and other objects. That's actually not that large for deep learning. Deep learning systems like the more data, the better they learn. So 60,000 is a typical smallish data set. You might want 100,000, 200,000, depending on the complexity of your problem. So, tens of thousands is normal and on the small side for the kinds of tasks that we might be doing. Fortunately, we don't have to gather these. We don't have to label them. Someone else has done all that work. We just grab the data and use it. So this first section, what we're going to do is to show you how you go about reading in the data set and then organizing it into training and validation data. And we're going to take a look at the data as well. So this section describes what's happening in the code block. I'm just going to do that and run it. So we have this, remember datasets was one of the things we imported. It's part of the Keras module. We say datasets.cifar10, which is the name of the dataset, .load data. Now, oops, I didn't mean to do that. One of the things that happens with datasets is that they are not always formatted in the same way. So there's always a period of figuring out what the data looks like that has to happen whenever you read in a data set. Now, I've already done this work for the data sets we're going to work with, and I will show you the result for this data set and then ask you to work through the results for the data set for the homework. So in this case, what the CIFAR10 data set returns, what you get when you do the load data, is a tuple containing two values. The first value has training data, and the second value has validation data. I should really call this valid data instead of test data. I was just being careless when I wrote this. So we can unpack those in this first step. We can grab the training data and separate it from the test data. The training data is itself a tuple. It has training images and training labels. So remember, this is supervised learning. We have the set of images of all of the animals. And then for each of those, we have a category. There are 10 categories. The labels will be numbers from 0 to 9 that represent the different categories that we might have. That's a standard, really common way to represent categories. We do the same with the test data. It has images and it has labels as well. Now, I want to know, for other reasons, how long the training data is, and since I know that the test labels are usually a NumPy array with a certain number of rows and one column, so each row represents a different example, and then the column is the label itself. The test images have the same number of rows, it's just that the data that's in each row is more complicated. It's the actual image. So I'm just going to grab the training size right there as the length of the training labels, just because I know I want it later. Oops, I did not run this first one. Let's go back. I'm going to run this. Takes a little bit of time because TensorFlow is a large module, and so is OpenCV, and honestly, so is Matplotlib. So it takes a little while to load these different pieces. It'll show you a little check mark on the left to indicate that it's done. Now we're going to rerun this section. And notice it is actually downloading data from the web. It shows you the website where it's getting the data. All right, that took about 45 seconds to a minute, but it did indeed download the data set. That's really slow. It probably will be much faster on campus. I'm here at my house. So now we have this data. You can actually look at it, and that's what we're actually going to do next. So the next section is exploring the data. And again, I've edited this. I've added some text here to try to explain the different pieces of it. I'm just going to talk through that for now. So I'm printing out train size here just so we can see it. And then we're going to look at what type of data train images is and what type of data train labels is. Test images and test labels should be the same type of data. And then I'm looking at what shapes they are. I'm going to print those out. And the last thing I'm doing is I'm grabbing one of the images and I'm printing its shape, which kind of depended on me knowing what the shape of the other data was, but that's okay. So I am going to now run this. It ran very quickly. So it says the number of training instances is 50,000. So we had 60,000. We kept 10,000 of those for the validation data, and we're using 50,000 for the training data. That's not an uncommon percentage. It's usually somewhere between 70 to 80% that you have as training data and the remainder as validation data. If you look at the types that these are, the train images is a NumPy array, and so is train labels. This is actually helpful for us. We've been working with NumPy arrays all semester. The shape of the training data is 50,000, so 50,000 rows. Each row contains a 32 by 32 by 3 image. So it has a little tiny color image stored in it. That makes it a 4-dimensional object. Don't try real hard to imagine what it looks like in space. Just think of it as rows and then images stored inside each row. And you can see that the labels, the correct answers, are 50,000 rows, but only one piece of data, one number, which is those numbers from 0 to 9 that give the categories. Validation data is the other 10,000, exactly the same shape otherwise, except for the change in the number of rows. And if I pull out row 0 of my training images, which I did right here, I grab the 0th element and I ask what shape it is. It tells me it's 32 by 32 by 3. That's the size of image that we're feeding into our model. All right, the next couple of steps, first of all, I'm going to define a list. I just want to have a word that represents each of the different objects. There are 10 of these. They correspond to the numbers from 0 through 9. So by their position in this list, the index of their position corresponds to the number. So if I have a label of 0, that's an airplane. If I have a label of 3, that's 0, 1, 2, 3, that's a cat. If I have a label of 8, that's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, that's a ship. This just allows me to associate those numbers really easily with a string that's more descriptive, so we don't have to memorize which number goes with which kind of object. This next script is going to display 25 random images drawn from the data set, from the training data. We set up a figure with this step. 10 by 10 I think is a unit of distance. It didn't seem quite like inches, but seems too big for centimeters, so I'm not sure what 10 of what is, but it basically sets up the overall size of the figure as it's going to appear on the page. And then we're going to loop 25 times. Each time through, we're going to grab a random index, a random row index into our training data. So it'll be 0 through 499,999. And then that's the image we're going to display. So we're adding a new subplot. So each of the little boxes you see down below from the last time I ran this, each of those is a subplot in the overall figure. You don't have to understand what the rest of this is doing, but there is a function in the matplotlib called imshow, which displays an image. So we grab training images and we select the one at the random index that we've chosen, and we say display this as an image. Note, we're reading these images in from a data set. These are not being read in by OpenCV. So the representation of these images is RGB, red, green, blue, not blue, green, red. It makes a difference if you show images with OpenCV's imshow that are RGB, the color looks weird, and similarly if you take a OpenCV red image and you display it with matplotlib, the colors will look weird if you're not careful. All right, the last couple steps, we are going to grab the label that corresponds to the value that we want. So we tell it the row. I think I can do this like this. So I'm going to do that. And then just to get the actual number out, I don't want an array. If I don't do this, I might get like slicing, where I get like an array containing the number. No, if I add the 0 here, I guarantee that I'm going to get the actual number as the value for label. And then we're using that as an index into our class names list and adding that as a label here. So let's run this again. Class names is not defined. I thought I ran it. Oh, well, if I didn't, I have to do it now. I'll try it again. All right, so there you can see the objects. We have frogs and birds and planes and deer and ships, cars, lots of horses, and so forth. Quite small images, very pixelated, not a lot of detail, but it is a good test set because it's not a super big problem. Again, you won't have to actually understand every line of this. You'll be just making a few changes here and there to make it work with a different data set later on. All right, pre-processing is the next stage in the process. There are many different ways that this gets done. We'll see a few of them. We're going to keep it really simple. Sometimes you have to resize images. You have to make them a size that's suitable for training with your model. Sometimes we want to add noise to them, do some of what's called data augmentation, where you like twist, rotate, move, translate, change the brightness, do things to make a small data set seem like a larger data set by making variations on each image. We're not really going to do any of that. We are just rescaling the data. So the original data as read in, the values go from 0 to 255. We are dividing by 255.0, which converts them into floating point numbers between 0 and 1. And that just turns out to be what the model wants. It makes life easier to put data like that into the model. So we do that for our training images and also for our test images. I should run that code before I forget. All right, so I just ran those two little lines. The next step is going to build the model. And again, I've been adding text so you can read it too about what each step in the model does. I'm just going to talk through it. One of the things I'll note is all of these extra inputs that you see that are getting passed to some of these functions, you don't have to understand those. Just put them in as they are and don't change them. That will be just fine. I want to just talk about the main purpose of each of these lines. So we're setting up a variable called model. It is a sequential model. What that means in the Keras TensorFlow terms is this model will be a sequence of layers, each one connected to the one that follows, all in a row. No branching. So if you remember the picture of the inception model, it had those little parts where it branched and then things would come back together again after a couple of steps. We're not doing any of that. A sequential model is simple. It's just a sequence of layers. And then we just have to specify each layer as we want it to be. So model.add adds a layer to our sequential model that comes adds it to the end. So we can specify the layers in order, and that's how they'll get added to the model. Input is just a typical first layer. It specifies the size of the input. There are some other things you can do with it. We're not going to. So 32 by 32 by 3, that's what this model is going to expect. The next layers you see here are convolutional layers. We talked about this in an earlier video, what that means. You really only need to look at the first two inputs here. We have the number 32, and then we have 3, 3. 3, 3 is the neighborhood size that we're using, and 3 by 3 is really common for these convolutional filters in this kind of a network. You will see others. You can experiment with trying other things, but 3 by 3 tends to be what we want. The number at the beginning, that 32, that's saying how many filters are there in this layer. So remember, when we have a convolutional layer, we can have multiple different filters. They each operate independent of the others. They can't see what the others are doing. They each have their own kernel that has initially random weights in it, and they do the convolutional process on the input image and produce their own feature map. And then we take all of those feature maps from, in this case, 32 different filters, and we squish them all together as one big three-dimensional array. And that's the data that is the output of this layer. Well, we run it through this ReLU function, but you don't have to know the details of that. So 32 different filters, each operating on a neighborhood size of 3 by 3. If you want to know what ReLU does, it just makes any negative values go to 0, and it leaves the positive values alone. The rest of this has to do with technical details, like how we initialize the random values initially and so forth. We have here 2 convolutional layers in a row and then a pooling layer. This is very similar to the VGG model that I showed in an earlier video. So we have 32 filters in the first one. That means we'll have a 32 channel image that comes out of that layer, and we're going to feed that entire thing into another convolutional layer with 32 more filters. Same size, 32 filters, each of them operating on 3 by 3. The result that comes out of that will be 32 more images, and those get passed then to the max pooling layer, and that's going to scale the image down. So it has 2 by 2 patches. These are not overlapping, unlike the convolution stuff where we looked at every possible overlapping neighborhood. Here we're dividing the image into patches that don't overlap. And we're saying for every 2 by 2 patch, pick the largest value, and that's the only one that goes into the answer. So, sorry about that. So what that means is if we have 4 pixels, a 2 by 2 section, and we only keep one value, a 2 by 2 section in the original goes to a 1 by 1 in the new one. So we end up with half as wide, half as tall. But we'll still have 32 channels because that's what comes out of the convolutional layer. Then what you see is we do this again. We have 2 more convolutional layers, the same neighborhood size, but now each one's got 64 filters. And these filters are looking at all 32 channels of the other image. And then we do that twice, 2 layers of 64 convolutions. We do another max pooling, which divides the data down one more time, so it's half the size it was before. We had 32 initially. After we do this max pooling, we're talking about roughly 16 by 16. After we do max pooling again, we're talking about 8 by 8. But quite deep, 8 by 8 by 64 deep. And then we're doing another layer where we have 128 filters per layer. And we do that twice. We do another max pooling down to 4 by 4, but very, very deep. You might notice there's some commented out dropout layers. We won't put those back in unless we need them. Those are to help with overfitting. We need to run the thing and see if it's going to learn at all. And then we can worry about whether it's overfitting or not. Once we're done with all of this feature finding, we get to the flatten layer. This marks the transition from the feature finding part of the model to the part that's actually doing the classification. Flatten doesn't do there's nothing learned about flatten. It just takes whatever block of data you have at that point and it unravels it and it turns it into a one-dimensional array. That one-dimensional array then connects to a dense layer that is 128 long. Every unit in the dense layer can see every unit in the in the previous layer, in the flattened layer, and it's looking for patterns in that data, in that vector. If we're lucky, the feature finding has made data in this vector that we're looking at that actually have useful patterns that will help us to identify the categories. Maybe it has some units that have identified ears and another unit that identifies water, and between those you can figure out whether something is a deer or a ship or something like that. It's very hard for us to read. We can't really tell what these models are actually looking for. We have to experimentally study that after the fact. All right, this then is a hidden layer. It just sits there and it looks for patterns, and then we pass on all of that information to the last layer. It's another dense layer, which means every output unit here can see all of the previous layer to make its decision. We need this number to be the same as the number of categories. So we have 10 categories with cifr 10. We need 10 units in our last layer. And we typically set this last layer, instead of being ReLU, which we've been using throughout, we set it to be softmax. We talked a little bit about that in the earlier video. Then there's also a helpful, once you build the model, there's a helpful function called summary that just prints a nice looking version of it. I'm going to run this code. I did run the previous block, I think. So this is an up-to-date thing. It shows you the shape of the data as it comes out of each of these. So 32 by 32 by 32, and then again 32 by 32 by 32. Then we go to 16 by 16 by 32, and so forth and so forth and so forth. And in the end, the flattened layer produces a vector that's 2048 long. It's 4 by 4 by 128. Multiply it out. So this just gives us a sense of the model and of how much there is that the model can learn at each different point. So you places where you see zeros, there's no learning that happens with those layers. They just process the data. But the convolutional layers have features that are learned, and so do the dense layers at the end. So those are what gets updated when we train the model on the data. Oof, that's a lot. All right, we're almost there. The next step is the most important, which is running the model. We need to tell the system what kind of algorithm we want it to use and what kind of metrics we want it to be tracking. So that's what this next section is doing. We say model.compile, and we specify which optimizer algorithm we want it to use. We're just going to stick with Atom. There are others. One's called stochastic gradient descent, SGD. There's some others beyond that. Just stick with Atom. It's a perfectly nice one. It's very commonly used. We need to tell it how to calculate loss. So that this string here specifies one particular loss function. I will tell you what to use for the second half. Cross entropy is the most common used loss function for classification tasks. And then we're doing categorical cross entropy because we have multiple categories. It's not just a binary categorization where you have 2 categories. We have 10. So categorical cross entropy is built for more than 2 categories. And sparse here means we're putting in the outputs as instead of putting them in as a vector that's 10 long to match the actual output of the model, we're putting in those numbers 0 through 9, which is just a condensed representation. So the model needs to know that, so it knows how to interpret those numbers in figuring out what the loss is. We are also going to track the accuracy as well. You could add more metrics here, precision, recall, other sorts of things that we do with machine learning, but we're just going to do accuracy. That's all we really need. So I'm going to run this. It will compile the model. Now we're ready to train it. The next step is to train the model. You can see I ran it a little earlier. There are a bunch of things going on here I kind of want to talk through. So here's our model. Fit is the name of the function that we use to train the model. It comes from statistics. We're fitting a function to the data is the idea. The function in this case is this big neural network thing that's super complicated, but we just use the word fit. We pass it then the training data, the input to the model, which is the images, and the labels that correspond to those images. That's a required input. In some formats, you can put that in as only one piece of data. In others, you put them in as separate pieces of data like I've done here. The system figures it out whichever way you need to go. We are then specifying how many epochs to train the data. I'm only going to train it for, I think I'll set it to be 5. Ugh. We are also telling it, oh, and I have some validation data. If I pass in validation data, then the fit function will automatically run the validation data every time we've gone through our data set. So one of the things that happens when you train neural networks is you have to present the data over and over and over and over for it to learn. And so we call one pass through our training data, we call that one epoch. And so at the end of every epoch, the fit function will also then run the validation data through the model without learning and report out how well the model performs on the validation data. So we get not just at the end of our training do we see what's happening, but we can see what's happening all along the way, one epoch at a time. With a simple problem like this, you might only need to run 20 epochs. With more complicated problems, you can run up to hundreds or even thousands of epochs to train a model. That takes a really long time, as you'll realize once you actually start doing it. Notice that the model function is returning a value here. It's returning this thing called history. We don't have to know all the details of what history does, but it basically captures the loss and the accuracy of the model at each point in the training process, at each epoch. So at the end of the epoch, it calculates the average loss over that epoch, and it also calculates the average loss for the validation data, and it computes the accuracy for the training data and the validation data, and it will report those. And we can then use this history value to graph the performance of the model as it runs. Let's try this and just see what it does, just so you can see it running. Don't pop that up. So it's setting up the model right now, it's getting things going, and then it will start training. Now notice it's running really fast. There's a timer there showing us about how many seconds till the epoch is done. There will be a delay once it gets done with the training data because it's running the validation data as well. It doesn't take very long because there's not a lot of it. And we're on to the next epoch. If you are running this and you get much slower performance, check your runtime. You might possibly be running it without a GPU to help you out. GPUs are great for this because GPUs are optimized to do things with images, which are, as we know, arrays. And they're optimized to do linear algebra operations because that's what we need to process images. So they are perfect for then doing this kind of work, which also is basically big arrays of data that need to be processed. All right, so let's look at what the results are right here. It tells you how long it took to run each epoch. It's showing you these are probably batches, so it put in chunks of images at once to the model, and it's called doing a batch. It doesn't actually update the model until the end of the batch. So it divided our 50,000 training images into 1,563 batches that were roughly equal size. What you see out here are the accuracy and loss of the training data. If it doesn't say anything, if it just says accuracy and loss, that's on the training data. And then it shows us the validation accuracy and loss. So you see loss is pretty high at the beginning, but if you watch it, it is decreasing over these 5 epochs in both validation data and in the training data. And you can see that the accuracy started off for the training data, it was only at 37%. It rose rapidly to almost 84%. Validation accuracy changed less. It went from 64% to 75%, which could just reflect that for whatever reason this time the random split of data into training and validation, it just happens to be a little easier than the training data itself. If we wanted to visualize this as a graph, the history variable holds it. So what I've got in this next section is this graph is not correct yet because I haven't rerun it. So we'll just close that. This is again using the matplotlib tools to plot the accuracy and the validation accuracy on the same axes. I'm going to run it. So what you see here, this is the training accuracy, and you see the validation accuracy, which isn't growing as fast. This is not bad as a gap, but I suspect that the model's not done. 5 epochs is not enough. All right, so then I'm going to actually show the loss as well. So here you can see I'm selecting out loss and validation loss. And you see the blue line is loss. That's decreasing the way we want it to. Validation loss is decreasing less, which is sort of expected. What I notice here is that this is by the end of the of epoch 4, when we get to epoch 5, the line is still pretty vertical. It's still dropping. What we want to do is to train the model until things kind of settle out. So what will happen is loss will be decreasing for a while, and then it'll kind of flatten out, and you get diminishing returns from doing additional testing. You don't improve the loss that much. And the same thing will happen if I scroll back up with the accuracy. So the accuracy will increase, and then it'll kind of flatten out, and you're not really getting any big increase in accuracy with additional epochs. You want to run the model enough that you see that happening with the training data, if not with the validation data. Here we're not really seeing that yet. 5 epochs is not enough. I could go back up here. If I don't really care about the graph, I can go back up here. I could click this button again, and it would continue training the data from where the model was left off, because I haven't told it, oh, reset the weights. The resetting of the weights, the initializing of the weights to random values, that happens way up where we created the model. And if I don't click that button again and run that block, then I'm going to be using the model I already have with the weights as they have changed, and I can see the result. It does mean that the history is incomplete, because it's only going to show me the most recent 5 epochs and not the whole thing. So if I do that, we'll just let it run. But you can see that we're getting better, right? We're up into the 90s in our accuracy. So 90% of the time, 93% of the time, it's giving the correct answer. It's not getting that much better with the validation. That doesn't look so great for us. You look at the difference in loss between the training data and the validation data, and you can see that the loss is now actually increasing. It went from 0.79, now we're up to 0.96, and we haven't really increased in accuracy in that time. This is a sign to me that this is probably overfitting. So what is going on here? Well, with this particular initial set of random weights, the model is overfitting. I would want to run this, because it doesn't take very long to run this, I would want to go back, change this epochs to maybe 15, and run it again from scratch so I can see the whole graph. But I suspect this model is overfitting, and we're going to need to do something about it. Okay, so this has talked through the activity we're going to do. I don't want you to be too intimidated by this. There's a lot of new looking code, but again, you don't have to understand every detail. You just need to get the gist of it so that you can work with it and modify the code a little bit and try it out on a new example. That's pretty much how I learned this. I took an example and I ran with it, and then I tried a different example and learned what I had to do differently. And I will be there right alongside you to help as you give a try to actually training deep learning models. I will see you all very soon.